Hi everybody and welcome to today's video. So we're going to talk about the binomial theorem. This is going to be quite a short set of videos, and what we'll do is we'll talk about some constructs like Pascal's triangle and the binomial coefficients first, and then we'll introduce the binomial theorem and do some exercises with it. So in order to get started, let's have a look at expanding powers of certain expressions. So what I'll do is I'll take the sum of two things, a plus b, and raise it to a power, and then have a look at what comes out. So if we raise a plus b to the power 0, we get 1, because anything raised to the power 0, other than 0 itself, gives you 1. Now we can keep going with the exponent, a plus b to the power 1. That's just a plus b. A plus b to the power 2 is a squared plus 2ab plus b squared. A plus b to the power 3 is a to the power 3 plus 3a squared b plus 3a b squared plus b to the power 3. We can do one more. A plus b to the power 4 is equal to a to the 4 plus 4a3b plus 6a squared b squared plus 4ab to the power 3 plus b to the power 4. And now let's have a look at these coefficients that we have in front of each of these terms. So we see that we have powers of a and b, and then certain coefficients in the triangle. So let's have a look. So for the first expression we have a coefficient 1, so we can write that here. Then for the second we basically have another 1 times a and 1 times b. So here we have 1 and 1. And then for the third we have 1a squared, 2ab, 1b squared, so 1, 2, 1, and then 1, 3, 3, 1. One, 4, 6, 4, 1. And now let's have a look at just the coefficients, and I hope a pattern starts becoming clear. So we see we get this triangle of numbers, and on the outside, the sides of the triangle, we have all ones. So we can use that to deduce the next layer in the triangle. There's probably going to be a 1 here and a 1 here. So we always get more numbers in deeper layers of the triangle, and 1 at the end. And then if you look at the inside of the triangle, what you see is that each number is basically the sum of the previous two numbers. So the 4 here is 1 plus 3, two numbers above it. The 6 here is 3 plus 3. This 3 itself is 2 plus 1. So in each case you take the sum of the two numbers above it, that gives you a new number. So in that case we can continue the next layer of the triangle. So 1 plus 4 gives us 5. 4 plus 6 gives us 10. 6 plus 4 another 10. 4 plus 1 5, and then we have that one. And now if we go back to our original expansion in terms of powers, if you do a plus b to the power 5, and I encourage you to work this out independently, what you'll find is that the result is 1 times a to the power 5 plus 5 times a to the power 4 times b plus 10 times a to the power 3b squared plus 10 times a squared b to the power 3 plus 5 times a b to the power 4 plus 1 times b to the power 5. And so what you see is that the coefficients in this triangle tell you what the coefficients are in this series expansion. And so this triangle is very important for all sorts of combinatorial purposes, and therefore it has a different name, special name. It's called Pascal's triangle, after the French mathematician Blaise Pascal. And using the triangle, you can quickly expand basically any sum of two things to raise to a power. So let's, for instance, do a plus b to the power 7. Well, in order to do that, we have to complete 2 more rows in our triangle. So, and by the way, let me also denote the powers associated to it. So this was what we had for power 0, power 1, 2, 3, 4, 5. And now we're going to need layer 6 and 7 in the triangle. And if you fill that out, you will get 1, 6, 15, 20, 15, 6, 1. That's for power 6 here. And 1, 7, 21, 35, 35, another 21, 7, and then another one here for layer number 7. And so the coefficients then tell us what the series expansion is, so we get... So I paused the video there so that you didn't have to watch me write down all of these terms, but what you see once more is that the coefficients here are precisely the numbers that you get from Pascal's triangle. By the way, Pascal's triangle is not just an invention from Pascal in the 16th century. This is something that is widely known in all sorts of mathematical texts. So there's a classical Chinese text from the 13th century where you can see a version of this triangle, and the mathematician Euclid in Greece knew a version of this in the 2nd century before Christ, and the Indian mathematicians knew this sometime between the 6th and the 12th century. So anytime that people started counting things and thinking about properties of sums and exponents, they discovered this triangle. Now, the triangle is good to calculate things out, and let's do maybe one example that is slightly less synthetic than a plus b. So we do 2x plus 1 over x to the power 5. What does that give us? Well, we go look in our triangle again for the coefficients associated with degree 5. Those are these coefficients, and then we just add them to our expression. So we get 2x to the 5, 5 times 2x to the 4, 1 over x to the power 1, 10 times 2x to the power 3, 1x squared, plus 10 times 2x squared, 1 over x to the power 3, 5 times 2x to the power 1, 1 over x to the power 4, plus 1 over x to the power 5. And now if you clean up the coefficients a bit, you get 32x to the 5, 80x to the power 3, plus 80x, plus 40 divided by x, plus 10 divided by x to the power 3, plus 1 over x to the power 5. So application of the Pascal's triangle coefficients, but now a is 2x and b is 1 over x.